like I said, I wouldn't go through, at the end of the last video, I said I wouldn't make a video of these solutions. But now that I've written them up, there are some really good points that I've made that I think that I just want to make sure that you do read them and note them. Always think about the future possible integration questions, and I think this is really good point here. And you could do this with every question. Think about what you've got to identify in a question like this, and you can see there what I've listed. Even I think this point here is a really critical one, that the numerator was an 8, but within that 8 we can see it as a 4 times 2, the 2 being the critical number because that was the square root of the a squared, which is the 4 in the actual question. But anyway, it'll make more sense if you've actually read through these solutions, when that the points I've made there. And of course, then when you get to these, anytime it's getting messy, just revert back to this. I think anything messy, you've got this technique. dy dx is dy du times du dx, and just use that. So that worked really nicely on that example. It worked on that example, and it worked on the next one. I just think anytime it's getting complicated, go to the simpler form to differentiate. And going back to, and again, this is not going to make much sense if you haven't looked through this question, but if you were asked to integrate that, that's a bit of a would be really nasty. Likewise, this next one would be really nasty. However, I think they will be probably more likely. I don't know if that's even, they would be more likely to be integration by substitution type questions, and we'll talk about that. We did touch on it last year, but I didn't go into it in much detail. I think the other extension class did, but because it becomes a whole little exercise by itself, then we will come to that. And again, when we've done that, what I'm saying back here in this question will make more sense. Okay, let's go on to the derivative of cos. So the derivative of cos, the only difference is it's got a minus sign. What can you deduce about the integral of the negative 1 over x squared? Well, it's going to have an inverse trig in it. There's nothing obvious in here that suggests that the integral of this expression would go to trig. It's all in what you see in the question. So that's similar. The proof of the derivative is similar to that of the sine inverse, and if you want to go through it, you can. It's in your textbook. So we've got the variations, that the derivative of cos inverse of x on a is minus 1 over a squared minus x squared. Now, that does not appear on the reference sheet. If we just jump back, it goes from sine inverse to tan inverse. So there is nothing about cos inverse. It's again one that you've really got to know. I guess you could set your integral up and take it back to sine inverse. But again, you'll see that when we do integration. And cos inverse would be of this format, just like sine inverse was. And again, use it only when you've got exactly AX. You'll see back in the examples when they were getting more complicated, for example, 2x plus 3, all in a bracket squared. That was too complicated, and this doesn't work nicely in that situation. So differentiating cos inverse e to the minus 3x, getting complicated. Introduce the u, and y then is cos inverse of u. Using dy dx is dy du times du dx. We can